will be presented by Mr. Jack Beswick from Jacobs Company, the UK.
Good afternoon, everyone. I'm Jack Beswick from Jacobs. We're a consultancy. Our head office is in the US, but I work out of Warrington in the UK, which is between Manchester and Liverpool. We perform testing and analysis of nuclear materials in general in my area of the business. I'm going to talk to you today about a testing program we've been carrying out to generate crack growth rates for alloy 600. The testing was designed to investigate the effects of both environmental fatigue and SCC on each other. So to do that, the main way we've been able to investigate the interplay is to carry out trapezoidal loading stages. So we will have a fatigue loading stage, but include a hold time in that. The talk today is comparing the crack growth rate data that I've extracted from my tests against two different laws which are used to predict these crack growth rates. So we've got NUREG 6964, which was developed by Argonne National Laboratory in the US, and ASME Boiler and Pressure Vessels Code 11, non-mandatory Appendix C. So here is a set of quite boring looking equations. They're used to predict air fatigue rates in a kind of Paris law type of regime. We've then got an environmental factor, so when we're in the primary water environment of a pressurized water reactor, we've got this additional term which allows us to assess the fatigue crack growth rates under those conditions. We've also got a primary water stress corrosion cracking rate, and then finally a law which allows us to evaluate the effects of both, so the combination of the two. If you actually look at these and you're very good at maths, you'll notice that they're all exactly the same, set for in the ASME 11 law. They set a rise time cap, and that's kind of what we're going to be looking at today. So the testing was carried out on 12.5mm thick CT specimens, oriented as shown with respect to the original forging that we've got. We've generated pure fatigue data, so we're just investigating fatigue loading, and then we've also carried out separate tests where we've combined and included these trapezoidal loading stages. We've investigated the material in both the as received condition and in a 15% cold forge condition to increase susceptibility to SCC. So here it's just a summary of the fatigue loading. We've tried two different R ratios, an R.1 and R.7, various different temperatures and various different hold times. You'll see that only the 50 and the 500 second rise time are above the 30-second rise time cap in ASME. So the ASME and NUREG documents both provide the exact same air predictions. What we're seeing is that the air predictions are quite good. This is on 15% cold forged material, so that there's a tiny bit of an enhancement, but the predictions are very good for both of these laws for this heat of alloy 600. When we then test in the environment, we can start to see the discrepancy between the two laws when this rise time cap is enforced. And the other thing we can see is that we've got a bit more enhancement over the predicted rates than we got with just air fatigue. So after carrying out these baseline fatigue tests, we've then carried out the combined SCC and fatigue test, where we've included the rise time. So that's in these two stages. It's pretty difficult to see, but we've got 500-second rise and then a 1,000-second hold, and then a 500-second rise and a 9,000-second hold. The idea of these stages is not only to investigate the effects of the hold time in the fatigue loading, but also it allows us to transition to a fully engaged SCC crack before carrying out our final constant load stage where we can get our SCC crack growth rate. So here we can see the difference between the ASME and the Nureg rate. As we've got increasing rise time, we can see that the Nureg prediction, which does not cap the rise time, using just fatigue predictions, offers a very good prediction of the test, whereas the ASME, when the rise time cap is enforced, we become inaccurate as we've got an increase in either rise or rise plus hold time. So if we consider just the Nureg law, which showed good agreement last time, in the last slide we included the hold time in the predictions, but this shows that if we take the hold time out of the predictions, then our predictions are starting to behave like the ASME rate, so we need to consider something else to be able to use these predictions. So what we do is we calculate the predicted SCC rate using the equation, which again was the same for both ASME and Nureg, but what we saw was that our test measured rate was actually much slower than the prediction. But taking the Nureg prediction, what we can then do is add that on to the SCC aspect of the trapezoidal loading stages. So when we've got a 1,000-second hole, we add on 1,000 seconds of SCC to our fatigue DA by DN to give us a rate for that particular cycle. And we can see here that in both cases, adding the SCC into the fatigue rate again gives us a very good prediction, and we start to be quite conservative with our crack growth rate predictions because we're now sitting below the line on these points where we've had the SCC contribution. But what we can see as well is that with ASME, with the rise time cap, which is this point here, these few points here, we're still not getting as good a predictions as Nureg, which omits the rise time cap and includes the full rise time in the crack growth rate predictions. So that was a summary of where we're up to with the testing. It's an incomplete testing program at this point. What the tests that we've currently completed, but we've not yet post-test corrected the data. We've tested 15% cold forged material under the combined SCC and fatigue loading, so we can turn up the SCC. We've done it at a higher temperature as well, so we've turned up the SCC in this test to really be able to pick out the contribution of SCC in these trapezoidal loading stages. And we've also gone back into fatigue stages as well after that. And the idea is once this test data is complete, we can then take any sort of conclusions and observations from the high SCC test and apply it to this, the one that I just showed, which had lower susceptibility. As just a short note here as well on some of the earlier tests that we carried out. So we observed very large grains on the fracture surface, and it made the post-test correction of our DCPD data very difficult to use for crack growth rates, because we saw very significant out-of-plane growth. So this is the fracture profile from the end of the pre-crack. So I've normalized different points along the fracture surface to the end of the pre-crack, and what we're seeing is 45 degrees, potentially even more out-of-plane growth. Excuse me. there's just an EBSD image of one of the tests where this happened. So we've gone to the end of the pre-crack, and then what we can see is that we have some transgranular growth caused by the earlier fatigue stages, but then when we start to introduce these hold times and these longer rise times where SCC becomes a contributor, we're getting intergranular growth, and the intergranular appears to be affected and kind of biased towards this very large grain. And we saw this on a lot of the tests that we carried out on the material with this inhomogeneous microstructure. So what we had to do was to get around this was to find a new heat of material which had a more homogeneous microstructure, so that when we were growing into granular, we carried on in a straight line. But it's just an interesting point that we've observed from the testing. Again, this is just a 3D heat map of the fracture surface, and we can see the influence of the large grains. It's taken this massive chunk out of the fracture surface, and this is all caused by these large grains that we observed in this particular heat of material. So the conclusions are there. I've been through them, but the main one is that the ASME and NUREG laws offers quite good predictions, provided we include our SCC contribution in a trapezoidal loading stage. If we include the hold time as in the rise time with the fatigue NUREG law, then that's also offers quite good contributions. And the large grains, if you find those in your alloy 600, they're likely to cause significant outplane crack growth as well. So thank you, and any questions or comments?
Thank you for the nice presentation.